was for those of you who may have made our seminar, and who missed the hour of sleep. I have to tell this little story. We used to have a similar thing when I taught at the UT Space Institute, and they always gave them in the big hall. You know, I mean, it was a big thing with a balcony. I mean, and the whole thing. And most of the students would get underneath the balcony where it was dark. and you know, get an hour of sleep. And of course, I cannot blame them, because most of the seminars were about somebody's dissertation research, and they were the only one who really gave a damn about it. Everybody else did. And I said, you know, if we're going to have these things, we ought to have them given at about a high school level. That way everybody can understand what's going on, as opposed to, you know, somebody giving his dissertation research and giving everybody whiplash from going to sleep. But anyway, for those of you who may have attended when we talked about the jet wing airplane at the seminar, this is a powered lift airplane that I had to, I don't know whether I call it an opportunity to fly or not, but I've got about 120 hours in the airplane. And it's powered lift, a very small airplane, wingspan about like from the end of this table to the wall total.
Is that a BD-100?
No, it wasn't a BD. This was built by the Ball Corporation. You know, the folks who make beer cans and satellites. Okay. Actually, Ball Corporation built the first satellite that left the solar system. Okay, they were the manufacturer of that satellite. The guy who ran that division was a fellow by the name of Pete Bartow at the time. And Pete was an airplane designer too, and he had designed a home-built airplane called the Scoyote. And some of you may have seen it. It very much resembled a de Havilland Tiger Bomb. Biplane, basically unstable, that sort of thing. Pete seemed to like unstable airplanes. The jet wing was also unstable, and for those of you who took stability control last time, we talked about it and that sort of thing. But anyway, the performance method is quite different. And also, if you look at today, you know, today we're starting to talk about, I personally don't believe these are going to be successful. We're talking about, you know, Uber's going to build an airplane that's going to take off vertically and transition to flight and all that. You know, I mean, there's 2 or 3 companies out there doing this sort of thing right now. This Z Aero outfit, most of them are on the West Coast. Most of them are tied to the tech industry. But you know, they're gonna fix things. At least that's what they say. However, having been in the airplane business for most of my adult life, I don't believe it. Okay, because you have to build a lot of airplanes, and I don't think the average human wants a machine flying them through the air, a machine that they have no control over, and that's what a lot of them are talking about. I'm sorry, you know, I mean, we kind of like tech, but we also like our skin, and we don't want to trust it to anything by ourselves. I mean, you know, that's driverless vehicles. I'm not real high on driverless vehicles. I don't know about the rest of you, but you know, I mean, I kind of like to drive when I drive. You know, I like to do it myself, and I really like to fly my airplane myself. Okay, I don't want a computer doing that for me. And so I'm not sure these will succeed, but all of these vehicles that they're currently talking about, you know, if this is the surface of the earth, they want to take off vertically. Now, we can handle that flight test wise, okay? We'll talk about, for those of you who take helicopter course next semester, we'll talk about this phase of flight if you're going to take off vertically. And by the way, if you're going to do vertical takeoff, do it in a helicopter. Because it is all about the disc area. Because the change in velocity across the rotor, the smaller that is, the more efficient that vertical flight is. The way not to do it was with a jet engine that's about that big around, you know. I mean, even the V-22, which has two pretty good sized rotors, when the Marines exit it, they get blown away because the downwash velocity is about 100 miles an hour. You know, it's like stepping out into a Category 3 hurricane. And so, you know, they get blown away. And that's got a fairly large disc area. Well, you take that and shrink it down to the size of the jet engine like the Marines F-35B.
Yeah, the nozzle that points at the ground.
And a nozzle that points at the ground, it blows our concrete away. So if you can, the thing of it is, if you can roll 10 feet, roll 10 feet. You know, if you can have any forward velocity, do it. But a lot of people are out there not trying to do that. So you have this thing, and then you transition to horizontal flight. Well, what do you do in this area right here? How do you measure the performance in that area? You know, we've talked about in this class how we measure it here. So we'll talk in helicopters about measuring it there. But how do you measure it from here to here? Well, that's what we're going to talk about today, okay? Yes, sir.
Now that we're talking tilt rudder, how is Augusta Westland going to handle the 609 when it comes to certification?
Well, they have already did, and there was a paper at the, I can't remember if it was this year's SETP or previous, last year ago's. They had actually been in horizontal flight, failed both engines, transitioned to an auto rotation, and landed the helicopter successfully.
Do they have enough mats to do a rotation?
Yeah. Yeah, the two guys, in fact, one of the guys who did that's a former student of mine.
Pretty good choice.
Okay, and they gave a paper on it, I guess
It was this year.
before last.
It was this year.
It wasn't this year?
Yeah.
Okay.
You know,
Yeah. But they transitioned that thing from horizontal flight to this and managed to successfully land it in
What else?
auto rotation.
he's within the dead curve zone, about 500 feet, a couple of.
Yeah, it seems like it was fairly, you know, very low, but they had to demonstrate it and actually demonstrated and gave a paper on
What is it? So you're talking about what is it?
it. The 609, which is a tilt rotor.
Tilt rudder version.
Yeah.
It's Augusta Westland.
Yeah, Augusta, Bell started it and then Bell
They sold it, yeah.
No, they sold it to Augusta.
And he's been doing it forever, right? Because we did the first
Yes,
121.
yes, they had one crash, fairly recent.
Recently.
Yeah.
What was it?
I have never heard exactly what the problem was on that crash, but they did have one crash. But anyway, an auto rotation from horizontal flight has been demonstrated.
What about CERT?
They're headed that way. It may take a while, you know, one of the problems is
Or you use 27?
with the FAA is a single failure. If you have one of those cross drive shafts fail, how do you get that by the FAA? See, that's a question that I don't think has been answered yet, because the FAA, if it takes two failures, the FAA don't consider two failures. But if it's just a single failure, it's pretty hard for them to get it certified.
What about regs? Do you use 27, do you use 20?
Both, you use both.
You use both.
Yeah, they're using both regs. However, like I say, neither reg talks about that.
So that's where the gap is.
Yeah, that's where the gap is. So that's the kind of thing we're talking about here when we talk about airspeed versus flight path angle. That counts for it. So for a powered lift airplane, both lift and drag are functions of if it has a blowing coefficient, or, you know, in the case of, you can call it the thrust coefficient if you want. In this case, with the jet wing airplane, all of the engine air, both fan bypass air and core exhaust, was ducted to the upper surface of the wing and blown over the upper surface of the wing. And it had, like I say, a very small wingspan. You know, I mean, the wings were, you know, fuselage was about this wide, and that was the wings. And it weighed 3,700 pounds with me in a parachute and full gas.
So it's really similar to a BD-100.
Well,
Size-wise.
it was size-wise. The engine and inlet was a nacelle from a Cessna Citation 1. Okay? And the engine, you know, fan, and it had two Y ducts, one that took the cold air to the outboard portion of the wing and slot nozzle about this high along the span of the wing, and the inboard portion, the hot air through a Y duct was blown over the inboard portion. It had a Coenda flap, a constant radius flap, that covered, well, pretty much all of the engine air was blown over the flap.
Could you get the flow to stay?
Oh, yeah, the flow would stay attached, certainly to, flap deflections of 45 degrees. The problem was that at higher flap deflections above, well, at 45 degrees, you got a tail stall. When you put the flaps down, as the past 45 degrees of deflection, the tail stall, and you ended up looking at the ground like this. But that was using an airfoil section on the tail that was essentially a symmetrical 8% thick section. So really didn't have any kind of needed inverted cambered airfoil in order to handle that kind of downwash. But in any case, what happens performance-wise is that, you know, everything we've said here, prior to this, we've said that thrust is equal to drag, right? And lift is equal to weight. You know, with small angle assumptions thrown in. But essentially, we assumed that thrust didn't play a role in lift, and weight didn't play a role in the drag of the airplane, other than power off kind of thing. So, how do we handle that when we have it? You know, in a conventional jet method of W over delta doesn't work, because the assumption in that is that CL is not a function of thrust. And you know, the purpose of W over delta, like PIW, VIW, was to be able to normalize the data into a single curve. That's good for all altitudes and what have you for a given set of conditions. So we need something else, you know, that doesn't care if thrust is tied up in lift and that sort of thing. And that method's called V-gamma, or airspeed versus flight path angle. And essentially for a given thrust, flight path angle, gamma, is a function of airspeed. And that level of excess thrust for each combination, you know, V gamma defines a relationship of a level of excess thrust for each combination of airspeed and flight path angle. And we can then, once we know that, the excess thrust can be converted into common performance parameters. One of the interesting things about this little jet wing airplane, it had been in the Ames 40 by 80 tunnel full scale. It was small enough you could use a whole airplane in there. And so I had, in addition to having the airplane, I had a full wind tunnel data to go with it, including thrust cow, you know, lift and drag. And one of the interesting things about the thing was say if this is a normal drag curve, well, when you added thrust into the mix, it started doing this. And what to me was very interested in this is that these curves at the top tended to go like that. So if you really just took a conventional airplane and plotted this up, say for this much thrust, the curve would look something like this. So you had all of this area that was usable to do things that nobody else could do. Like turn, maneuver, accelerate, that sort of thing. You know, I mean, we've spent a lot of effort developing vectored thrust. But this would be a vectored thrust airplane right here. A powered lift airplane. Because a vectored thrust airplane is still stalled when it's stalled. Powered lift airplane isn't. So you have all of this area to be able to maneuver. So if you were a fighter jockey in a powered lift airplane, where would you want to go? You don't want to go in this area because nobody else can turn with you. Unfortunately, we haven't understood that. And you'll see a reason why in a bit, okay? So if you do this, if you have excess thrust, you can convert that into performance parameters we've already talked about. You know, like rate of climb, acceleration, max level flight speed, what have you. And since climb, acceleration, and level flight's a function of excess thrust can be determined by flight tests using either as a flight test technique. Well, steady climb, we've seen these equations before. The flight path angle, the sine of the flight path angle is just the rate of climb over the true airspeed. Okay? And the excess thrust is the gross thrust of the airplane minus the drag, and that happens to be equal to the weight times the sine of the flight path angle. This is a case for a steady climb. And here's a plot that looks somewhat like what you all did, except yours went up. This one is just a fixed thrust, and in this case, it resulted in a minus 390 feet per minute rate of descent. So what and this is from the jet wing airplane. One of the reasons this airplane was longitudinally unstable, and I would, rather than try to use a level acceleration, which could be used in a stable airplane, with an unstable airplane, it was somewhat easier to spend your time sweeping out the cockpit with a stick to keep the airplane stable while you did a climb or a descent than it was to try to do an acceleration where things are changing rapidly all the time, you know. So we used a rate climb, and this is just one of them. This was done this is altitude starting here, going up to 8,000 feet. Altitude versus time, with an indicated airspeed of 175 knots and a thrust setting of 80% in one. So I would just set the thrust on the engine. In this case, it was a fan engine, and N1 was the best thrust reference, so I would use set N1, set the airspeed with this thing. Okay, here was thrust, here's airspeed, and then I would, you know, time it, and the way I would, I had telemetry for this program. I would squeeze the trigger on the stick, which was the radio, and say, okay, you know, altitude is such and such, thrust is so forth. And a nice grad student on the ground would write that stuff down. Because I could not write it down since it took both hands to fly the airplane. And, you know, that was the telemetry, was radio.
How hard was the flight?
I'm sorry?
How hard was the flight there?